Okay, everybody. So we are on section 3 of Unit 6, and this is all about preserving distances. Okay, and we're talking just specifically about transformations that preserve distances. Right. So from this, you should be able to describe a sequence of transformations and be able to determine if or not the distance between the two any points on those objects were maintained. The distance was preserved. Right. So if I have like an object like this, and then we dilate it, or we transform, or this underwent a transformation, like it rotated, it dilated, it reflected, or it translated. If all of these lengths here stayed the same length, okay, and then if I'd be able to draw some sequences given like algebraic description, some points, right, and then be able to say, yeah, did they after doing all that, was distance preserved, right? And then identify, given some things, after if I shown some transformations, did it or did it not preserve distance, right? So again, preserving distance, or strictly speaking of line segment lengths. Right, so you already know that I have two major types of transformations. Right, I have rigid or isometric. Right? Well, sorry, rigid and isometric, also known as isometric. Sorry about that. A trick, right? And those are rigid and isometric. Those are, rotations, reflections. That's a bad symbol for reflections. That's a reflection. Yeah, that's a reflection-ish kind of reflection. And then I have like a translation. Yeah, it's a translation. That's a translation. Okay? And then I have dilations, which this whole chapter is about. Right? So when we do any of these, right, this maintains congruency. Maintained. Therefore, line segment lengths and angles are congruent, right? These similarity is maintained. Therefore, only angle measures are congruent. Right, so from what you remember from unit 1, right? Dilations, like line segments, aren't congruent. Nope. So dilations will not preserve distance, whereas the rest of these will preserve distance. So rigid transformations, also known as isometric transformations, rotations, reflections, translations, preserve distance. Dilations do not. So that's just that's like the whole meat and potatoes right there, but let's show you how to kind of do the homework. Well, this is the homework, but the practice work. Okay, I don't know if I can zoom in a little bit and still get you to see everything. Okay, so I have these images, right? This is my pre-image, and then this is my image, right? And it's going to have me write all of these, plot these, and then determine what happened. And I'm gonna like write the algebraic expression and everything. Like if I can just look at these two, I can tell you what happened right away. Right? If I could look at my Q and my Q prime, right? My X and my Y was -1. My X and my after X, or my prime X coordinate was 2, right? And then my Y for Q was 2, and then it was 1 here. Right, so if I just do a simple point comparison, I can see that my X's and my Y's flopped, and what was my X, right, turned flopped signs. Right, so that is the tail end of an algebraic expression, which would be so when my X's and my Y's flopped and one of them turns negative, that's a rotation. When the X turns negative, that is a clockwise rotation of 90 degrees. Right, so rotations of when the X's and the Y's flop, it's a 90-degree rotation. When one of them is negative. Okay, when the X is negative, it's a clockwise rotation of 90 degrees. So I know what to expect here. Okay, so let me go ahead and plot. So what type of rotation was applied? I mean, do I even need to plot it? I mean, I'm gonna plot it, but just to prove that I was right. Right, but let's see. I'm gonna say it's a clockwise rotation of 90 degrees, and it did this preserve distance. Yes, it sure did, because it is a rigid motion transformation. All right, so let's see. Let's put some rubber to the road here. All right, so my Q value, my Q is -1, comma 2. This is Q. R is -3, 1. R and S is 4, -4 and 4. This is S. Okay, so I'm going to take this here. The only way for this to really rotate it and still stay on the page is to rotate clockwise, which is tick, 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 tick this way. Okay, so now I'm going to plot my other one. My Q is 2, 1. It's now Q prime. R became 1, 3, 1, 3, which is R prime. And S is now 4, 4. And that is, oh, that's 1, 4. 4, 4 is up here. This is S. S prime. So now you can just draw that guy there, connect all the dots. Got my super high-tech 97 cents multi-function straight edge here. UL listed. There we go. So that is my rotation. And to prove it even further, I can go 90 degrees from just pick a point. I'm gonna do Q because that's gonna illustrate my image even more. Pick a point, Q, even use a different color. To Q to my origin, because I rotated about the origin. And you will see that it is a 90 rotated clockwise. So, bingo, bango. There you go. It is a 90 degrees clockwise rotation. All right, I was able to figure that out using just a simple point comparison. Right, when you do your point comparison, make sure the absolute values of your x and y are different. Otherwise, it's going to be more challenging. If your x's and your y's flop, and one of them is negative, it's a 90-degree rotation. When the x is negative, it's clockwise. When the y is negative, it's counterclockwise. Just think x, the negative side is this way, it goes this way. When it's this way, it goes this way. That's the easy way to remember it. Negative sign pushes it one way or the other. So that's the way I remember it. So, okay, so now our next thing is we're going to put a scale factor from our primes. It's going to go from prime to double prime. And our point of dilation is the origin. All right, and our scale factor is 1/2. So our going to be x comma y. I do this in blue, or blue anywhere. Pink. Pink would be nice. X comma y. Okay. And it'll be x, y, and we'll do a 1/2. Alright, so that means that each one of these, the x value and the y value, is going to get reduced by half. So I'll start with my q. Okay, my q was at 2. Now it's going to be at 1. This is going to be my q prime, double prime sub x. Right, and then it was at 1. And now it's going to be at 1/2. So this is going to be my q double prime sub y. So now it's going to be right here. So this is q double prime. Alright, my r was at 1. So now it's going to be at there. So it's going to be, this is going to be r double prime sub x. And then it was at 3. So now this is going to be r double prime sub y. So now it's going to be 1, yep, 1.5, which is right here. Oh wait, no, that doesn't seem right. 1. Oh wait, q should be here. Sorry about that. This is q prime sub x. Q prime. Right, so then we have r prime sub x should be right here. R prime's right there because r prime sub x and sub y. Okay. Then we have 4 and 4. That should be 2 and 2. That one's pretty easy. I'm not gonna write it on that one. That double prime. Okay. So now I'm going to take my straight edge and connect my dilations right through my point. Oh well, right through my label. And there we go. There is now my point. Right, and I can calculate, make sure that I can actually take, make sure that I did it right. There's 1. There's 2. And 3 is going to pretty much go right to it. And there's 3. Okay, so there's my all centered at the point of origin there. Okay, and so I know that I did it right. So there's my after my dilation, and you can see there that it was no, it was not preserved. No, not preserved. It was a dilation, therefore not a rigid motion / transformation. Okay, there you go. All right, moving on to this page. All right, so this one is even easier. Okay, this image was recorded by this was a dilation. Right, pretty obvious dilation, so it did not preserve distance. I'm wondering what the scale factor was. Well, this was, let's see, 1/2. My x to z is 1/2. This is my x prime to z prime was 1/2. I'm just looking at the length of x, y to z prime. Okay, and my length of x to z was 1, right? So my scale factor was equals my z to x prime, or prime. This is bonus stuff. Divided by my z to x, which equals 0.5 divided by 1, which equals 1/2. Okay, I multiply both sides by 2 to clear that. So my scale factor was 1/2. Okay, I could also went from here to here. That's 0.5. That's 0.5 distances long, and that's that's 1 long, and this is 2 long, so it's 1 divided by 2. And you could also have like figured out the distance from here to here, a distance from here to here, but there's lots of ways to do that. Lots of ways to figure out scale factor. Okay. All right, this is a reflection. Pretty obvious reflection. If you weren't sure, you can pick any of the points, right? You can do a point comparison. You can go z and then z prime. Z is z was -1, 2. Z prime was 1, 2. My x's and my y's are the same, except my x flopped. Right, so my x's and the y's are the same. That's and then one of them change. It's a reflection across an axis. This one is a reflection across the y-axis because x changed and y stayed the same. Okay, and this one does preserve distance. That one preserved distance. All right, so here is a rotation. Okay, that's what my gut tells me, but I'll do a point comparison just to be sure. My y value, I'll choose y. My y was -3, 1. That's my y value. My y prime is 1, 3. Point comparison yields that y and x flopped. My x value changed from negative to positive, right? So this is a 90-degree rotation because x and y flopped, and the negative sign is in front of the x, so it pushed it this way. Because it's on this side, it pushed it this way. It's a clockwise rotation. Clockwise rotation. So this is a rotation, and rotations do preserve distance because everything is the same length. See, everything on this one, everything on this one's the same length. This one, everything was not the same length, right? Because I divided it. everything. Why did I write the thing there? It should have been written right there. No, it's fine. All right, so this one here, everything is facing the same way, right? Nothing's reflected, nothing's rotated. Everything just seems to have moved over and right. So that's a translation, right? If I wanted to figure out, looks like it's over 1 and down 1. So my delta x is +1, my delta y is -1. Right, so that's kind of cool, right? And then I would, so this does preserve distance, right? Because this is still 1, and this is 1, right? This is 2, this is 2, right? 1 squared plus is 4, or 1 squared is 1, 2 squared is 4, 4 plus 1 is 5, the square root of 5 is the square root of 5, so both of these are still the square root of 5. That is math. That's Pythagorean's theorem, right? So there's that one. So this is that one, okay? All right, so here's 2 tiny little triangles. They are both, they both have the same, all the same lengths of 1. 1 squared plus 1 squared is 1 plus 1 squared is 1. They're all 1 unit in length. Okay. So, actually, this is the square root of 2. Sorry, 2 square root of 2. 1 squared plus 1 squared is 2. That's the square root of 2. Each one of these little blocks is a square root of 2. Alright, so there's a cool little thing for you guys to keep in mind, because if you keep adding these up, it's square root of 2. But anyway, so this is a reflection. Oh, this is different. It was either by a reflection, okay, or this could have been couldn't have been a translation. It could have been a rotation, right? Because it could have been, because it doesn't give us any points, right? So it could have been a reflection where we have.
I thought you didn't do a word.
That was my wife asking why I wasn't doing any work. So, this is my, so I'm here doing, what was I doing? Oh yeah, so this could be a rotation too, right? So I could have had these two here at a 90-degree angle that rotated clockwise 90 degrees or counterclockwise 90 degrees. It doesn't really matter which one. Okay, so this could have been a rotation or a reflection, and they do preserve distance. Okay, all right, so that is homework. That is lesson 3. Pretty straightforward and easy. Hopefully that makes sense.